Every layer of the global computing infrastructure, from neural network server clusters to secure defense microprocessors, relies on a single, uncompromising physical foundation: the monocrystalline silicon wafer. Producing these wafers requires growing massive, flawless silicon ingots from a liquid state at temperatures exceeding 1400 degrees Celsius. At these extreme thermal thresholds, the slightest deviation of even half a degree can trigger dislocation defects within the growing crystal lattice, rendering an entire multi-million-dollar batch completely useless. In 2026, the elite venture funds and sovereign entities financing semiconductor independence are realizing that controlling software design means nothing without absolute dominance over the underlying materials science. Consequently, billions of dollars are being poured into optoelectronic pyrometry infrastructure to mathematically govern the molten thermodynamic phase transitions that dictate the future of computing capital. The foundational science of this high-temperature process relies on the physics of blackbody radiation and non-contact thermal imaging. Inside a Czochralski growth furnace, a quartz crucible holds molten silicon, while a seed crystal is slowly withdrawn and rotated to form a uniform ingot cylinder. Because the molten silicon is highly reactive, placing a physical temperature probe inside the liquid is impossible, as it would instantly melt or introduce fatal chemical impurities into the crystal matrix. To bypass this barrier, engineers utilize optoelectronic pyrometers mounted outside the sealed vacuum chamber. These sensors capture the invisible infrared and near-infrared photons naturally emitted by the glowing, superheated liquid. By passing this light through specific optical filters and focusing it onto high-sensitivity silicon or indium gallium arsenide photodiodes, the system converts the raw kinetic energy of the photons into a precise electrical signal, mapping the exact thermal field of the melt in real time. The direct financial utility of this optoelectronic tracking is the elimination of catastrophic asset depreciation inside heavy semiconductor foundries. For institutional infrastructure investors, the capital expenditure required to run a single crystal pulling facility is immense, with a single batch production run wiping out weeks of operational yield. By integrating multi-wavelength ratio pyrometry into the automated furnace control loops, facilities can instantly calculate the true thermodynamic temperature of the silicon, completely independent of changing surface emissivity or vapor clouds inside the chamber. This absolute measurement accuracy allows automated factories to maintain flawless structural uniformity throughout the hours-long growth process, locking down the exact geometric and atomic tolerances required to guarantee high-margin wafer yields for premium tech portfolios. However, scaling these non-contact optical sensors to operate continuously within high-throughput industrial environments introduces severe engineering and materials constraints. Over days of continuous melting, volatile silicon monoxide vapors inevitably escape the crucible, coating the furnace's internal quartz observation windows with a thin, hazy film. This microscopic deposition scatters the outgoing infrared light, artificially dimming the signal reaching the external pyrometer and causing the automated system to read a false temperature drop. To protect the optical path without breaking the ultra-high vacuum chamber seal, instrument engineers deploy specialized gas-purged optical sights that continuously blast a laminar stream of high-purity argon gas across the inner surface of the lens, dynamically deflecting volatile particulates away from the optical axis. This convergence of optoelectronic pyrometry and semiconductor material assets represents a permanent shift in how sovereign technological security is secured. Capital is moving past speculative consumer software applications and anchoring its long-term valuations directly to the physical purity of the atomic substrate. The corporate syndicates currently financing the deployment of advanced multispectral thermal sensors and automated crystal pulling foundries are establishing an unassailable gatekeeper position over the hardware layer of modern civilization. The survival of high-tier technology portfolios now depends entirely on mastering the thermodynamic radiation curves of molten matter, proving that the ultimate guarantor of commercial dominance remains rooted in the absolute laws of optical physics and solid-state engineering.